Hello, welcome back. Can you hear me okay?
Yep.
Cool. Sorry about the delay. I kind of gave into the peer pressure. You said you were having lunch, and I thought maybe I should have a little something too, so I apologize for that.
No problem. Because my dad just came and dropped some off, and I haven't really eaten anything. So yeah, that's the only reason why I was eating lunch just now.
Yeah, makes sense to me. The only thing I've eaten was well, I guess technically I didn't eat it. It's my normal morning cup of coffee. That's my breakfast. So I
Huh.
just make
Wow, just coffee?
just coffee. Yep, that's it.
Wow, that's you're a soldier. I don't know.
So what are we doing today? Do you have any questions about anything so far? Anything we've covered?
Yeah. I did my homework yesterday, and I know I have one.
All right,
I
absolutely.
think. Wait a minute. Um, I'm gonna go back to the website. I may or may not have resolved it, but I doubt I did.
So the floor is yours. When you get the chance, feel free to write any problem you might have on the board.
Yep.
Let me make sure you have permission to annotate. You should have permission. Yeah, you
I
do.
typically do. Yeah.
Cool. All righty. How was your break?
It was pretty good actually. How was yours?
Really, really boring, to be honest with you. But I got to sleep a
Yeah.
lot, which is really nice.
Were you able to get out the house?
Yeah, I went to my friend's party. It lasted a couple days, and then I mostly just slept. I like sleeping a lot.
Wow, a couple of days?
Yep.
How does he threw a really big party?
It was at a hotel.
Oh, you can do that?
Apparently,
Wow, I didn't. Wow, okay. That sounds like fun.
it was fun. I saw a lot of people that I haven't seen in a really long time. And
Oh, like old friends.
yep, exactly. And before and after, I slept a lot because I was kind of sleep deprived. I haven't been really catching up on sleep, but I feel fresh as a daisy now. And I'm drinking more coffee as we speak. There's a mathematician named Paul Erdős who said that a mathematician is simply a device for converting coffee into theorems. And I think I agree.
So he's a relatively recent mathematician then, huh?
I think he was born, I think, in the early 1800s.
Yeah, that's sort of when coffee started coming around.
And it makes me wonder what the ancient Greeks and Romans and even my ancestors, the ancient Poles, what they did for their caffeine fix before coffee was around. Because they came up with some pretty cool math stuff too, math concepts.
I think it was alcohol, beer, because I remember one summer when I did my AP World History homework, I did this thing where it was the history of the world in 7 glasses, and it just talked about it placed all of world history in the context of the major or the most popular drink at the time. And it started out with even like with ancient Mayans drinking, alcohol made from fermented grains and whatnot. So if we're talking really long ago, that's what I think it would be.
Well, I can say from personal experience that beer does not help my mathematical abilities.
Yeah, see, that's a little no, not sure how that really helped them out, but I think it might have been nutrients or something.
Yeah.
Okay, so what was that?
Oh, I was just saying I can see how that might help. So you found your problem that you were talking about?
I think so. It has to do with the natural log and just converting with the exponential form and whatnot. I don't remember, but it was just like it's confusing because there was something that I couldn't get down.
Do you remember enough about the problem to maybe write something like that on the board?
Oh, yeah, actually, yeah, I think okay. So my issue was resolved. Okay, it was the question that I texted you about yesterday, the one
Oh,
with
natural log of 11.
the natural log of 11.
It's a constant. The derivative of any constant is always just going to be 0.
Yeah, but what I wasn't realizing was that you had to apply chain rule. So I guess the way the derivative of the natural log works is if you have a variable that's when you set it as a fraction with it on the denominator. But I also, yeah, once again, the chain rule was, I didn't know the chain rule had to be there. So
Yeah, but you don't even really have to think about the chain rule that much. All you have to think about is if we're taking the derivative of something, we don't know what it is, something with respect to x. If this thing is a number, we don't even really need to think about the chain rule thing. All you need to do is ask yourself, is this a number or is it a function? Because if it's a function, you take the derivative the way you normally do. But if it's a number, it will automatically just become zero. You don't even need to think about the chain rule. Derivative of any number is zero.
mhm.
Same goes for sine of 2 pi or cosine of pi over 3. Anything with a definitive value has a derivative of 0.
Okay. Yeah. So yeah, the problem was something plus the natural log of 11, and it was like it involved the derivative as well. So I just, and I was getting the first part, but I wasn't getting 0 for the second part. So that's what was confusing me.
I see. I find myself saying that quite a bit when I was taking calc for the first time. That's what confused me. I found myself saying that quite a bit.
Yeah, the chain rule is just crazy.
For me, it was optimization that was the first time I had to take a breath in AP Calc and say to myself, whoa, what have I gotten myself into?
Yeah, it was optimization was, I don't know, I feel like optimization, I like optimization, and I like drawing and using the first, second derivative and their respective rules and stuff. I feel like I've done that so much that even if you use natural log and E in there, I could do it. But so optimization is pretty nice for me too, because it's a relatively simple concept once you have the other stuff down.
Well, your parents are mathematicians. My parents hate math, and everyone else in my family hates math too. So I don't really have the background for it.
My parents both know it because growing up in Romania, it's pretty much a
Well, I
part
know
of
you grew up
your.
in Romania.
They did. I was born here, but their education was in Romania, and I guess at the time it was just a lot harder than one that I have. So
Does your
you
last
know,
does your last name end in U?
yeah,
Okay, so I think most, if not all, of Romanian people have last names ending in U. I know a guy named
yeah,
Marcu and then a guy named Salcianu. They're both Romanian.
yeah. If it ends in a U, it's pretty good chance, pretty good bet.
Indeed. So, any other questions?
I'm gonna say no.
All right. So, do you want to practice optimization a little bit more?
Sure.
All righty. Let me open up my textbook here. All right. I found a good one. So this comes from my book. It says the top and bottom margins of a poster are each 6 centimeters and the side margins are each 4 centimeters. And I'll draw a picture of this when I'm finished reading. It tells us that the area of the printed material on the poster is fixed at 384 square centimeters. Find the dimensions of the poster with the smallest area. So we have the poster itself, and then we have printed material on the inside. We have side margins of 4, and then we have top and bottom margins of 6. So it might look something kind of like this. This would be 4. This would be 6. And then our interior area, the area of the picture itself is fixed at 384.
Mm-hmm.
And we are trying to minimize the area of the poster, minimize the area of the entire thing, printed and
The entire thing. Okay.
How do we want to set this up?
Well, we have a fixed 384, so that for sure. Yeah. Well, for optimization, we need like the constraint equation. Uh, and what else?
The thing that we're trying to optimize would be the other thing we need.
And yeah, the thing that we're trying to optimize. And so I think the constraint equation would be the formula of area for the actual picture itself.
Yeah.
And the thing we're trying to optimize is the other dimensions of the paper. So
Yep.
like everything on the outside.
Yep, exactly right. But that's not enough, though. We want to have equations for everything because we can't use calculus as a tool to help us solve problems unless we have things in algebra language, for lack of a better word. See if you can create equations for the constraint and the thing we want to optimize.
Constraint thing we want to optimize.
So the constraint is always going to be the thing that cannot change. And it would help if I could spell the word right. I have trouble with spelling, apparently. Excellent.
And then the other thing is, oh, I think the other equation is going to be b
You got it.
and then okay, yeah, and then this plus 12 is equal to.
Is that whole thing equal to 384 or only the? Oh, I see what you're doing.
It's equal to 384 plus plus what is it? Oh man, I
You know
actually
what
don't
might
know.
make things easier? It might make it easier if we generalize this and maybe just slap a variable on the right
Yeah,
side.
that would definitely be easier. We could just say A, I guess.
Yeah, it will work perfectly. All right, so what do we do from here?
Well, I think one thing that we want to find out for sure is the dimensions of the inner square and the dimensions of our final product.
Okay, go for it.
So I'll solve for H and then substitute it into the other equation.
Sounds great.
And now I'm going to assume that I can FOIL.
Yes.
And this is going to work out nicely, I think.
Yeah, it's one of those problems where it may not look like it works out that nicely, but then it comes together pretty well.
Okay. So we have this. And then I'm gonna, right, yeah, okay, so I'm gonna do.
So how come the 3072? Well, never mind. I see what you did. But then you could combine these together, couldn't you, and make things a little bit easier?
Yeah, yeah.
But actually, I agree with what you're doing, but wouldn't it make more sense to take the derivative first? Because then if you take the derivative first, this would be 0. You would have a 0 instead of AB, right? I mean, actually, I should stop talking now. I'm curious to see how this ends up. So continue. Sorry for the interruption.
Okay. No, but wait, why would we take the derivative at the first step?
Because then it just makes it a little bit easier to find a critical values because you have a derivative equal to 0 instead of equal to something else.
So we could treat that first step as like our whole function.
Yeah, you could.
Okay. I kind of wanted to change AB though into I will actually just change A into 384 plus DXS or
All
with
right,
the frame. Okay.
go for it. Here, I think I'm going to pause the recording just so we don't have a lot of empty space.
Yeah.
So you're saying that you wanted to change A, B into what exactly?
I wanted to change A into a constant so that I could combine like terms or just B to the one with the other B to the one coefficients.
Well, I haven't tried it that way. I'm not sure if it's possible without making things more complicated, because I can see one way where we might be able to do that. So for example, A would be this right here. This would just be, oh, we already have A. So you're probably thinking you would just, oh, that wouldn't work, because then we would have the same thing on both sides of the equation. We would have maybe this right here instead of this, and it would complicate things a little bit. So I've never actually tried to do it that way. I don't know if it'll work or not. It's possible that it might work, but the way I solve this myself is I combine my terms first. So I made this part into, well, if 384 plus 100 is 484, then 484 plus 96 is just going to be 480. So this is going to be 12b plus 12b plus 372 over b. Oh, sorry, 3072 over b is what I meant to say. And then plus 480. And I want to give myself a little more room here. And then this is equal to A. So then from there, I just took the derivative of everything. So the derivative of 12b is just 12. Derivative.
So this derivative is the derivative of A with respect to B?
Yep, exactly. It's the derivative of this entire thing with respect to B.
Okay.
So then the derivative of 3072 divided by B is going to be minus 3072 over B squared.
Mm-hmm.
And then the derivative of this constant is 0. And then A is also a constant. Or sorry, I didn't say that right. It's actually just dA dt.
Yeah.
dA dB is what I meant to say. Derivative of area with respect to B.
But then you set that equal to 0.
Yes,
then,
exactly.
Okay.
I just did that a bit prematurely, but that's what I was trying to do. So if we set that equal to 0 and then add this term to both sides, we get 12 equals 3072 divided by B squared. And then from there, it's just algebra we have to do. From there, it's just simply solving for B. Do you want to take it from here?
Yeah.
Have at it.
And now we have to put them through the tests, I believe.
So we may not even really need to do that, because let's just ask ourselves, what is B really quick? We know B is about.
Oh,
what does B represent in the problem?
It's a physical distance. It's the base of the interior square or rectangle, sorry.
Exactly. So what does that mean in terms of our solutions? Are they both valid, or are only some of them valid?
Only some of them, or only one of them.
Yep, exactly. We discard the negative. It just does not make sense to have a base that's negative distance.
Yeah, it's not physically possible.
Right. So now all we need to do is find h, now that we know what b is.
Right. So that's just gonna be, let's see, can I do? I think h is gonna be 24.
You are correct.
Okay, and so this minimizes the area of the whole thing.
Yep. And this is the correct answer, but I will say if you wanted to verify it, the second derivative test wouldn't work because if you take the second derivative of this thing right here, you would get something that's more complicated. It isn't going to be just a constant. So what you would rather do instead is probably make a sign chart. You would make a sign chart for the area with respect to b. We would identify the fact that when it's 16, we have a zero derivative. We would just pick a value that's less than 16, like maybe 0 or 1 would be easiest, and then a value greater than 16. Or even maybe just take the limit as the value approaches infinity. Think about what would happen if you plug infinity for b into our function. So we note that this would approach 0 right here, because if the denominator gets bigger and bigger and bigger, if it tends to infinity, this entire term right here would approach 0. So that's how we know this is decreasing. Or hang on a second, I have that wrong. But I did this problem, I think a week ago. It's in my notes somewhere, but this is the correct this is the correct height that minimizes the area, and then this is the correct base that minimizes the area.
Yeah, okay. Okay.
All right. Do you want to do any more of this? Because I think this is the last derivative concept I'm going to have us do in this class. What are you guys working on in your other class right now?
So you remember when I told you how pretty much I have this one page of notes, and it's like all the derivative rules of various functions and mathematical tools, or constants and things like that. And you gave those to me a while ago, and you gave them to me before I was even doing them in my own class. So now really what we're doing is just like derivatives, but they're involving Euler's number and natural log. And yeah, so it's pretty easy actually, because I already did it with you.
Yeah, that is interesting. It's April. When is the last day of your class?
It's May 16th.
How is that possible?
I don't know, but what I do know is that we have in the total course, there's, let me see here real quick. There's a total of oh, that makes sense. That makes a lot more sense. There's 6 chapters. We're about to finish the 4th one next week, and then we're gonna have a chapter 4 quiz on there. I'm looking at this and it skips chapter 5 for some reason, and then it goes to chapter 6, and then there's the final exam. So I'm assuming chapter 6 is going to be integrals, but yeah, it's crazy. These are these college courses, they're so much faster than regular courses, and I kind of appreciate it, but at the same time, it's crazy. But yeah.
Seems like you're skipping a lot. Like I went to UNR, and I'm actually going to be going back there again really soon to finish my electrical engineering degree. And I've tutored a lot of students in math who are taking Calc 1 and Calc 2. A lot of them don't skip chapter 5. Chapter 5, I assume, is just the applications of derivatives chapter. A lot of them just go through all of that, and typically I think they would be in antiderivatives by now. So your school's just doing things a little bit differently than UNR, and I think UNLV would do as well. But
this is CSN, so probably.
Yeah, that makes sense.
It's on my math lab.
Oh, mine was too. UNR uses my math lab too for calc classes.
I had Alex last semester. I don't know.
Oh, really?
That's like it's like math lab as well. I'm looking at the e-text right here. Applications of the derivative for me was actually chapter 2. Chapter 5
How
here.
can you apply derivatives before you learn derivatives, though? That's the thing. That's
I don't
boggles my mind. How can you apply you don't
applications of the derivative? It was just this was it actually. So it was describing graphs of functions using the first and second derivative rules, as well as using those rules to test and then sketch curves. And then it was optimization problems, further optimization problems. And then chapter 2.7 and 2.6 and 2.7 on the day of the quiz, that was the first time I looked at those because I forgot that the quiz didn't actually go over those two. So I was looking at these two chapters and I was seeing some crazy things that, we didn't do. And I was like, oh my God, but there was some crazy stuff. And it was like, business and economics applications. It was, but then chapter 3 is the stuff that you taught me, which is, quotient, product, and, chain rule. Uh, chapter 4 is what I'm doing right now, the exponential and natural logarithm functions. And it's just pretty much, converting these two into either their exponential or logarithm functions and then deriving them or taking the derivative of them and, just doing questions. Chapter 5, the one that we skip, is applications of the exponential and natural logarithm functions, which I'm not sure why we would, skip that, but it says here it's exponential growth and decay, which I've learned. I actually kind of like those. Compound interest, I also like those. Further exponential models, and then applications of natural logarithm function to economics. That's chapter 5 right there. And then we end on chapter 6, which is the definite integral. So we start integrals. Wow, that's kind of late if you ask me, but
Yeah, even in my high school calc class, we started integrals, I think, late November, maybe early December, like right before Christmas break.
wow, that's like 2 months after August. Yeah, that's like 2 months after school starts, 3 months.
Yeah,
That
and the reason
was
is because integrals are much, much, much harder than derivatives. Derivatives are clicky. They're easy to do. Maybe clicky isn't the right word, but they're easy. They're tedious.
yeah,
They take a lot of time and a lot of effort. They're frustrating, but you can take the derivative of anything easily.
yeah, yeah.
Integrals you can't say the same for.
Uh,
There are some things that you can't integrate, and there are some things that you'll try really, really hard to integrate, and you might just give up because they tend to be pretty complicated in some cases. So I
hmm.
think that's why we want to spend more time on integrals than we do derivatives. So I was thinking, if you don't have a problem with that, maybe we could start integration right about now. But you
Yeah,
did mention something about logs and Euler's number. So let's maybe review just a little bit of that, make sure we're good with all of that before we
yeah, yeah,
dive
yeah.
right in.
Okay.
So I want to give you two functions. This is one of them. And then this is the other. I'd like for you to take the derivative of both of these for me. See what you get.
All right. Hmm.
Well, I want to ask you real quick, do you think they're going to have the same derivative, or do you think the derivatives will be different?
I think the derivatives will be different.
Indeed.
The first one I can't. I don't know about the first one, but on the second one, Is the second one gonna be 0 or no?
No.
No?
Nope.
Okay. So then I think the second one is just,
So a thing with this kind of problem is doing a little bit of algebraic manipulation before we apply calculus, because it would make things a little bit easier for us. So I'm going to take the first one, I'm going to write it in a slightly different way to make it easier to understand what we have to do to take the derivative. So we have to use the chain rule. It may not be obvious that we have to use the chain rule when it's in this first form, but in the second form right here, it's pretty easy to tell. We have a clear outer function and we have a clear inner function. So we're going to apply the chain rule. We're going to move the 3 out front. We're going to subtract 1 from the exponent like this, while leaving the inner function alone. This becomes a 2, and then we're going to make this times the derivative of the instant.
isn't this just power rule for,
Power rule and chain rule together.
yeah, I see.
So this is the derivative of the first problem, the first function. And then I'm going to do a little bit of algebraic manipulation for the second one as well. There is one of those exponential, one of the logarithm rules that tell us that we can take an exponent that's being applied to the argument. It's being applied to the argument in this one, but not in the first one. Whenever it's being applied to the argument, you can take the 3, move it out front. And it kind of like the product rule for derivatives, but this isn't a calculus thing at all. This is just an algebra rule.
Yeah, it's just a property of logarithms.
Exactly.
Dang, I forgot about that.
So then we can just use the power rule. We're going to get 0 times natural log of x plus 3, plus 3 times the derivative of natural log, which is just 1 over x. So this is the derivative. This is dy dx. So maybe let's practice a few more of these before we dive into integrals, because these are going to be applied to integrals quite a bit.
Yeah, we probably should do that then.
Let's try this one. Getting ready for some inception. We're doing logarithms inside logarithms. Are you ready for this?
I should be.
That's the spirit. So see if you can find the derivative for us. And actually, you know what? I don't want to limit your writing space, so I'll let you write the notation when you're ready. Have at it. Have fun. As much as you can with this.
Let's see.
Oh, and sorry, I forgot to ask. You're still okay with doing the 2 hours today?
Yeah, I'm good with that.
All right, and then I just owe you, I guess, another hour for Tuesday then.
Yeah, so we'll just do like a double session Tuesday and we should be good.
Sounds good. Just putting another function up there for you to do when you're finished with the first one.
So just a quick question for the first one. It's pretty clear that we're gonna apply chain rule maybe once or twice, but so to apply the chain rule for the first time, it would be the derivative of the outer function, which would be the outermost natural log. When I do that, can I use that one trick, the where it's just the derivative of what's on the inside over the inside?
Yep, absolutely. U prime over U.
Okay. I actually was doing this, and my math lab showed me like the proof for it too.
Oh, really? That's cool.
Yeah, I don't remember it, but it was cool when I looked at it. Okay, I'm pretty sure both of these are gonna be wrong, but I don't know. There's like a bunch of different rules, and I'm not sure which ones to apply. So just gonna throw my best attempts out there.
All right, let's take a look. So the first one, I'm going to consider this entire thing to be our inner function. So we're going to do U prime over U. So we want to take the derivative of everything in the shaded box first of all. So I'm going to call this U. I want to find U prime. So we have to do U prime over U once again for this situation. So for the shaded, the interior function is going to be 2x to the fourth. That is U. And then the derivative of 2x to the fourth is going to be 8x to the third. So we have U prime. Now we have to do U prime over U. So U is going to be everything in the shaded. We have to put the derivative over everything in the shaded box. So this is going to be 8x to the third. Well, I'm going to simplify this. I'm going to make this just 4 over 1. Oh, actually, we can simplify a lot more than that, too. Let me just simplify this a little bit more. We can make this just 4 over x. Yep.
Or 4 over x, yeah.
4 over x. So we get 4 over x for U prime. We're going to put that over U. We're going to put that over everything in the shaded box.
Dang, this is
But then
oh,
I
and I
forgot
didn't
what part of the
simplify.
chain. Wait, hang on. U prime over U. Yeah, this is it. And then let's talk about the other one as well. So we can't do the same trick right away we did in the last one because we have cosine instead of a natural log. So we're going to apply the chain rule. The derivative of cosine is negative sine. We already have that. So we have negative sine. We're going to leave everything on the inside alone for now, just like we always do for the chain rule. And then we multiply by the derivative of everything we have inside. So I'm going to make another shaded box. And this is natural log. So we're going to apply u prime over u to take the derivative of everything in the argument of our cosine function. So in this case, we can see that u prime is going to have to be 12x squared. U prime is 12x squared, and then u is just 4x cubed. But we can simplify that a little bit. We can make this into 3 over 1. This is just going to be 3 over x. So I'm going to take the 3 over x. I'm going to move it out to the front just to make things look a little bit prettier. So we have negative 3 sine natural log of 4x cubed all over x. Oh, yeah, just like that.
Would that work?
Yeah. That's how we apply the chain rule.
Wouldn't there be an x, and wouldn't it be because you put everything over the same denominator, right?
Mhm.
So wouldn't you have an x being multiplied with what's on the left in the first line and then minus 3 all over x?
Oh, so this is a subtraction sign, sorry. This is this thing times.
Oh, whoops. Okay. All right. Yeah, that makes sense.
All right. So I was thinking maybe we could just start talking about integration right now, if that's all right with you. We're about at the 1 hour mark so far, almost there.
Yeah, let's do it.
So I want to start by asking, do you know what do you know about integrals? Do you know anything at all about them? Have you had maybe a preview from your teacher? What do you know about it?
No, all I can say is I'm assuming they're like something of some sort of opposite to derivatives.
You're absolutely right. They're connected by something called the fundamental theorem of calculus. And I'm not going to get too far into it, but there are two fundamental theorems of calculus. One of them establishes the integral as the opposite of the derivative. So we know derivatives give us rates of change. They give us a slope of tangent lines, tells us how fast something is changing. It gives us a rate of change. Now, what do you think an integral might give us? What kind of useful information can we get from an integral, similar to what a derivative gives us, do you think?
Probably like points on the graph that or data points, something like that.
You're on the right track. So derivatives tell us rates of change. Integrals tell us something that's so fundamentally different. An integral tells us the area under the curve of a function. So this is just some generic function. An integral tells us the exact area under a curve between two predetermined endpoints.
But what kind of in what units?
It depends on the situation. So if it's just a normal function, for example, what if we have, I don't know, maybe y equals sine of x, or just any function, they would just be square units. But if you're dealing with like an actual problem, like for example, if you're dealing with something like a related rates kind of a problem, you would have to look at the units given to determine the units of area.
And it always ends at the axis?
Always ends.
At the area, okay.
And I'm going to try not to screw this up. So I know I didn't draw it perfectly, but if you do it right, an integral gives you the 100% perfect area under the curve. And it's really nice because there are some things that we don't know how to take areas of.
Yeah,
Some things we do know how to, but other things we don't. So for example, if we have this expression, this function, I mean, what if we have, nope, I want to make that 4 minus,
but how is this the opposite of a derivative? Because derivative is like rate of change, but the area, I don't see how area would be the opposite to the rate of change at a certain point of a graph.
we're not going to be getting into that right away, but trust me, we will be getting into that.
Okay.
And it is mind-blowing. So we do know how to take the area of this. This is just the circle equation. This just gives us, if we were to integrate this, we would get the area going from this point to this point. And we don't even need calculus to find that area. It's just a normal geometry formula we learned a long time ago. So before we get into the algebraic part of integration, let's talk about ways to approximate area. And I don't want to spend a whole lot of time on this like a lot of other classes do, but I do want to give a proper introduction to what we call a Riemann sum.
What?
Riemann sum.
Sum. Oh, okay.
Suppose we have some function. I want to pick an easy one. I want to pick 1 plus x. And we wanted to find the area under the curve. And we could do it by making a triangle and then a rectangle. But for the sake of argument, what if we wanted to break it up into subdivisions instead? What if we wanted to make 4 different subdivisions, each of them with equal width? So I want to call the length of one of these subdivisions delta x. In fact, they're all going to be delta x. It's important that all 4 of them are equal width. So let's say we wanted to draw a rectangle only as far as the left endpoint could reach. So we're going to stop right here because the left endpoint can't reach any higher. And then we're going to do something similar right there. And then something similar right there. Then something similar right there. It's a pretty cruddy approximation, wouldn't you agree? We're missing out on all of this area right here.
Yeah.
All of this untapped area generates a pretty large margin of error, wouldn't you agree?
Mm-hmm.
So this isn't a very good approximation at all. But what if we alter delta x a little bit? What if we broke everything in half so that we have 8 subdivisions instead of 4 and then try again?
It'd be a little more accurate this time.
Exactly. Not at the level we want it to be, but I think we can agree it's a lot more accurate than it would be if we had just 4 subdivisions.
Yeah.
So my question to you is, do you think there's a perfect number of rectangles that gets us the exact 100% correct area that we're looking for?
No.
What makes you say that?
Well, these rectangles, no matter how many of them you draw, if it's the shape that you're drawing, the shape that you're inscribing them in, it just isn't made for them to fit perfectly. So no matter how many you draw, there will always be those little triangles that form at the uh, diagonal or the slanted, the top where they hit the line. So there's always going to be a margin of error, and that margin of error just decreases with the more rectangles you draw.
Okay, so we agree that 16 rectangles would give us a better area than 8. And we agree that 32 rectangles would give us a better area than 16. What if theoretically we had an infinite number of rectangles? Do you think that would give us that 100% area we're looking for? What if instead of a bunch of areas with a fixed width of delta x, what if we shrunk these rectangles, made them infinitely small, so that instead of having a fixed width like this, they're more like lines, and instead of delta x, it becomes dx, kind of like how it did with a derivative when we're bringing the slope of the secant line closer and closer until it became a tangent line. Theoretically, if we had rectangles that are infinitely thin, do you think we would have the area then?
I think that I think you'd get extremely close, so close that the difference where the margin of error is negligible. But if you have a line, lines technically don't have a width, And if you have, these rectangles that even though their width is so small that you couldn't see it with the human eye, all the way at the top, there will still be that very, 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 extremely tiny little um amount of area that you just don't hit with the rectangle. But like I said, even if you have infinite amount of those, I think that the difference or the amount of area that you're missing out on in the approximation becomes so small that it's negligible, and many people will just agree to use that as the official area of the triangle or of this figure specifically.
So for 1,000 rectangles, it's negligible. For 1,000,000 rectangles, it's even more negligible. For 100 million rectangles, it's still negligible. But what if we have infinity? What if we don't have a set number? If we have an infinite number of rectangles, there is zero margin of error. By that point, we no longer say it's negligible. We say that there is zero error whatsoever. There's zero margin of error. We have an infinite number of rectangles. And that's what the definite integral is based on. It's based on the idea of taking a Riemann sum and bringing the rectangle smaller and smaller and smaller. And we're cramming an infinite number of rectangles in a region. So I want to just provide you with the very first definition of the definite integral. So we use this symbol to show an integral. This is just the symbol that means we're taking the integral of some function.
Okay.
And then we have an endpoint. Our starting endpoint is A, our ending endpoint is B. We say that this definite integral is defined as being the limit of a Riemann sum. So we're taking the limit as n approaches infinity. And then n is just the number of rectangles. We're taking the number of rectangles to infinity.
Mm-hmm.
And then this right here is a Riemann sum. We're doing I equals 1 to n. So this just means we're adding together. Well, remember that n is infinity. We've established that we're taking n towards infinity. So we're adding together an infinite number of whatever I happen to put in this box right here.
Mm-hmm.
So let's talk about what we're adding together. So a rectangle has a base and a height. We know what the base is. We know that the base is delta x. We want to talk about what the height should be of this rectangle. So we know we take it higher and higher, higher, and we stopped right here. The reason we stopped right there is because that's the function height. So that means the height of the rectangle should be the function height at whatever this x value tends to be, whatever this x value is. So we just typically call that c sub I. I don't know why that is, but c sub I is the naming convention for this x value. So then this is going to be f of c sub I. This is going to be the function height when x equals c sub I. So that means the area of one rectangle is going to be delta x times f of c sub I. That's going to be the area of one rectangle. So f of c sub I times delta x. So this is the definite integral. This is how we find the area under the curve. And I'm not going to make you suffer by making you take integrals using this way, like my teacher made us do. There are integral rules that make things really easy to integrate, just like we have for derivatives. This is kind of like what we did for derivatives early on when we took the derivative by taking the limit as delta x approaches 0. Do you remember those days?
Yeah, I definitely do.
Well, those are relatively easy. This is a pain. It's a hassle. We're not going to do that in my class. I'm going to show you the integral rules straight away. We're not going to be really dealing with this, but
I mean, we could, because I mean, I don't know what my class is gonna do, so I wouldn't mind. That's all I'm trying to say is, if you really wanted to, we could.
Okay, I'll keep that in mind. But this is just the definition of the definite integral. So this just means we're taking the integral of some function f of x. And then you might be wondering where dx comes from. So let's talk about that real quick. So let's say we have the derivative of some function. Let's say we have dy dx is f of x. And let's say we want to do the opposite of taking the derivative. Let's say we go backwards. Let's say we want to find the function that has this derivative. it's easy if we know what it is. For example, if we know that if dy dx is e to the x, so what function has this derivative? What function's derivative is e to the x?
E to the x.
Is that the only one? What about e to the x plus 2? What is the derivative of e to the x plus 2?
It'd still be e to the x. So e to the x plus any constant.
Exactly right. So we don't know what the constant is. So whenever we take the integral of a function, we always have to put a constant there. We don't know what it is. But before we do that, let's talk about what to do next. So we're going to move dx to the other side. We're trying to integrate this to find the function. We're trying to find f of x. We're trying to find the derivative, the function that has this derivative. So we're going to multiply both sides by dx. We get dy is f of x times dx. And then this is just the convention for finding the function that has a given derivative. We always integrate both sides. And the integral of dy is always just y. So we have y is integral of f of x dx. And that's why we put the dx there. The dx comes from this differential equation that tells us that our function is dy dx. That's where that part comes from. Any questions?
Is this something I should be writing down?
Yeah, I would recommend you write this.
Okay. So actually, my one question is, so when you write dy over dx is equal to f of x, that was to demonstrate the Euler's number thing?
Well, this was to demonstrate why we put dx in the integral. So everything in this box is completely independent of all of this stuff.
Mm-hmm. Well, yeah, but if so, the only function that has its derivative as the regular function is e to the x, and then e to the x plus any constant. So why would you need the d of x when if you take like the derivative of a constant, it will always be 0?
That's correct. Derivative of a constant is always 0. So what was your question?
So why would you need the dx then?
At this part right here? Or at
no, at this part.
Oh.
Is this so you can get y?
Oh, it's because this is this right here is the area under the curve. Everything there is the area under the curve. Dx is the width of a rectangle. To find the area of a rectangle, remember you need a height, which is f of x, and you need a base. So without the base, you can't find the area under the curve. This is the height of one rectangle.
Is that d delta then?
This is, well, remember what happened when delta x gets infinitely small. When you take delta x to be infinitely small, it goes from delta x to dx. So dx is an infinitely small delta x. So with delta x, we have a fixed number of rectangles. With dx, we have an infinite number of rectangles. So that's where the dx comes from. This is the width of an infinitely small rectangle, and this is the height of an infinitely small rectangle. And then this symbol just means we're adding together all of these infinitely small rectangles.
Mm-hmm. Okay.
All right, let me know when you are ready to continue.
I'm ready.
All right. So let's talk about the concept of an antiderivative, because that's how we integrate functions. We integrate functions by taking the antiderivative of another function. let's say we have f of x is equal to cosine of 2x. No, sorry, just cosine of x. And we want to find lowercase f of x. And then we can say that big F of x is equal to the derivative of lowercase f of x. So if cosine were this, if cosine were this one, it'd be pretty easy to see that big F of x would just have to be negative sine of x. But how do we find that information if we are going backwards? If we have the function and we're trying to find the derivative of that function, how do we work backwards? How do we find an antiderivative instead of a derivative?
It's a good question. I'm not sure.
So we just want to think in terms of opposites. We want to ask ourselves, what function do we take the derivative of to get cosine?
Sine
Yes. And it's not just sine. Remember
of
what you
x,
said before
sine of
about
x.
there needs to be a constant there. We don't know what it is. We don't know. It could be sine of x plus 2, could be sine of x plus 3, could be sine of x plus pi, could be sine of x plus any constant under the sun. We have no idea what it is. So we put a c right there. We always put a c when we take the antiderivative because we don't know what constant may have been there originally.
Okay.
So let's put this in calculus notation. What we did right now is we took the antiderivative of cosine. So every time we integrate a function, we take its antiderivative. The antiderivative of cosine of x is sine of x plus c. Make sense so far?
So that sign that we use, that's also the symbol for antiderivatives?
Well, this is the symbol for an integral, but you always use an antiderivative to integrate a function. You can't take an integral without the antiderivative.
Okay.
How do we integrate x squared? How do we find the antiderivative of x squared?
Well, I guess first we assume that x squared is the derivative of an original function.
Exactly. It's the derivative of something. We're trying to find the thing that has this as its derivative.
And so since it's just x squared, I'm gonna assume that, power rule was used. And I'm gonna say that the original function was x cubed over 3.
You're exactly right.
And that's just reverse engineering the power rule, I
That's
guess.
exactly what we do. So you just integrated. You just integrated x squared, and our answer is x cubed plus over 3 plus c. That's how we do it.
And that's equal to some sort of area of a function.
Well, this isn't an area. This is just an antiderivative. In order to get the area, we need to have limits of integration. So we need a particular. So I'm glad you mentioned that. So let's maybe talk about how to find the area.
Okay.
Let's say we have the function y is 2 minus x squared. So we know we have, hang on, I want to make it 4 minus x squared. Sorry. And it looks like that. So let's say we want to find the area under the curve going from 0 all the way to 2, from x is equal to 0 to all the way down to x equals 2. We could do a Riemann sum. We could get some margin of error, but we want to just find the exact area. We don't want to have to deal with a margin of error. We want the exact thing. So we're going to integrate this expression. We're going to take the integral of 4 minus x squared. Whoa, what happened there?
That happens to me too.
Bit too excited, I guess. X squared dx. And now we need what we call limits of integration. So the limits of integration are the things we call our endpoints, the place we start and the place we stop.
So
we can
0 and 2.
we want. Yeah, in this case, it would be 0 and 2, but it doesn't always have to be. You could have just this region if you wanted. You could even go into the negative x values. You could maybe do here if you wanted to. And
why would you do that?
There are certain problems where they're going to ask you for areas that go beyond this region right here. So it all depends on the context of the problem. We're going to be using calculus. We're going to be using integrals to solve real world problems. And there are going to be certain situations where they want you to find areas of really particular regions. So it's good to be in the habit of doing that. It's good to know how to do that kind of thing. But then we could also do, this is going to look kind of strange, but we could also find areas going from, for example, what if we wanted to go 0 to 3? Well, in that case, we would have to make a line right there. And then everything between 2 and 3 would count as negative area. Everything between 0 and 2 would count as positive area. So anytime you have area above the x-axis, it's positive. Every time you have an area underneath the x-axis, we consider that to be negative.
And do you add and subtract those areas or no?
Yep, you always do the positive area minus the negative area. So an integral, that's how an integral computes area. This integral right here would consider this to be negative. But for example, if you had, like if you're taking an AP exam at school, if you were taking the AP Calc exam at school, a common question then for them to ask would be for you to find the area under the curve. They only want the area bounded by this. So you would have to find the place where it changes from positive to negative. You would have to take the absolute value of this part and then add it to that part. So if they just want the area, it's fine. If they just want the integral, it's fine to consider this negative. But if they want the total area, we'd have to convert this to make it positive and not negative. Yeah, like I said, it's really common to make you do that on the AP exam, but you're not going to have to worry about that. You're taking college calc, so we're going to practice it a little bit, but not as much as we normally would in my normal classes that I teach. So this is 4 minus x squared. So we want to integrate going from 0 to 2. Those are our limits of integration. And now I want to see if you can integrate this one for us. So we can integrate things term by term, just like we differentiate, just like we take derivatives. So we take the integral of 4 and then just take the integral of negative x squared. So let's see you do that for us.
So do like the same thing that I did with that other one with x squared?
Yep.
Okay.
Here, I'll give you a little bit of space. Here, let me move. Whoa. Here, I want to move my really nice looking picture. I put a lot of time and a lot of effort into this. I always miss something. I wonder if I should just quit and go to art school. I wonder how disappointed my parents are.
I don't know. You said they don't like math, so they might like art a little better.
Yeah, you're right. All right. Have at it. Nice. So you took the antiderivative the right way, but now we want to take it a step further. In order to find the area is going to be a number. What we have here is a function. The antiderivative is a function, but the area is going to be a number and not a function. So we're going to apply our limits of integration. So this is the second part of the fundamental theorem of calculus. It tells us that whenever we want to find the area under the curve, we just do, if we consider this part to be f, capital F of x, everything in brackets is capital F of x, the area is going to be capital F of b minus capital F of a. In this case, we can see that b is 2, and we can see that a is 0. So area is going to be 4 times x, that's going to be 4 times 2, minus 2 to the third power over 3.
Is this a rule that always applies though? The
Always
area
applies,
formula?
always applies to definite integral. So we call this a definite integral, where whenever we have limits of integration, like in this case, we have limits that are 0 and 2. This is a definite integral. If we didn't have limits of integration, this is an indefinite. We have, this is definite, this is indefinite. You have to take a definite integral to find the area. So we have capital F of b, and then we're going to do capital F of a. So we don't need plus c when we're doing definite integrals, but I want to show you exactly why we don't need plus c. I'm going to put plus c for now.
Actually, I had one quick question.
Sure. What's up?
So in the main one, we have 4 minus x squared dx, right? And then we also have y, which is our original function, which is like a lowercase f of x. And it's also 4 minus x squared. So when we take the antiderivative, why do we take the antiderivative? Because that's just like, it's like doing the opposite of the derivative to the original function, which, I don't like, why would we need to do that?
Because it's impossible to find the area under the curve without the antiderivative. Yeah, you're right. I want to make the notation a little more synonymous here. I want to make sure that I'm using notation that matches everything else. So I want to make this lowercase f of x. So capital F of x is the antiderivative. We always have to take the antiderivative to find the area under the curve. There is no other way. Just kind of be in the habit of making the connection between area under the curve and antiderivative. You can't take the area under the curve without the antiderivative. So we did a capital F of b. Now we're going to subtract capital F of a. So we're going to plug in a 0 for x instead of 2. So we're going to have 4 times a, so 4 times 0, minus a cubed, so 0 cubed over 3 plus c.
And just to confirm, the formula we have for area on screen, it always applies to definite integrals, right?
It only applies to this particular one. It always just depends on the antiderivative of whatever this is. You always take the derivative of everything in the antiderivative, sorry. Always take the antiderivative of everything in the box to find the area under the curve from going from A to B.
But the area in the end would still be like f of b minus f of a, right?
Always.
That will always apply to a definite integral?
Always.
Okay, thank you.
Yep. I don't think my drawing is helping us anymore. I think I want to just get rid of that and utilize the extra space. Well, what happened there? Amateur hour over here with me using the Zoom. So let's simplify things a little bit. We're going to get 8 minus 8/3 plus c, and then we're going to have minus 0. 4 times 0 is 0. Minus negative, so we're going to have plus 0. And then we're going to have minus c. So what do we get when we simplify this all the way, if we simplify this completely?
We get 16/3.
Yeah, exactly. What happened to the c?
They canceled out. We had a
Yes.
positive and a negative c.
So whenever you do a definite integral, the c's always cancel out. You only need the plus c when you do an indefinite integral. So whenever you're finding an area under the curve, that's a definite integral.
And that will, yeah, that makes sense because it'll always be a plus and a minus.
Yes, exactly.
So basically, there's no c needed for the antiderivative.
Correct.
Okay. This
But
is
having,
interesting.
yeah, I thought so too. When I first took calc, I didn't think this would be super useful in a lot of different situations. But what I'm studying electrical engineering, and you need integrals to find the circuit flow, and you need to use it to find resistance and all of these different things regarding electrical circuits. It's pretty interesting.
Wow, really?
Yeah, I'm a big geek about that kind of thing. I love electronics, and I love using math to model electronics. If you study, what do you think you might want to study as what's your major?
My major is biological sciences.
So you might even be using differential equations. So there's a class called Math 285 that's differential equations. You're going to be using derivatives and integrals to solve complex problems, which is really, really interesting. I really like that class.
You've taken it before?
Yeah, I took it in fall of 2014. Damn, I'm old. I didn't
Wow, that
realize how
was a
long ago
while
it
ago.
was.
That was 7 years ago.
I know, right? I can't
It's
believe
crazy.
I feel
Wait, so what kind of problems need this kind of stuff though? For in terms of like biological sciences?
well, I'm not too sure. I mean, I've never really studied biology except in high school, but
Hmm.
my understanding is that we use integrals to model populations in certain biomes, for example. Like if you
Hmm.
have a population curve given by some generic looking graph like this, you can use an integral to find the increase of a population in a certain biome by taking the area under the curve. And that's about all I know. Like I said, I've never really studied bio. I've just talked to people who have. Some of my mathnasium coworkers are into bio, and we've talked about this a little bit, but that's the extent of my knowledge regarding math and bio together.
Hmm.
So
Okay.
let's see if you can integrate this for us, dx over x. It's different than the ones we've seen before. What do you want to do here? What does it look like we want to do?
Well, in this case, it looks like our actual original function is so basically what the notes that I've taken down, it shows that for the actual right next to the symbol, you'll always have your f of x, lowercase f of x, and then dx.
Mhm.
And so I would rewrite that as 1 over x or x to the -1, and then I guess times dx. And since we're taking the antiderivative, I'm pretty sure that's just going to be a natural log of x as our capital F of x.
Perfect. Exactly right. That trips up a lot of people, but you knew right away that this was just, yeah, I'll let you write.
Oh, my bad.
I,
Okay, I'll write it. Ln of x. Yeah.
but there's one thing we need to put because this is an indefinite integral.
Oh, okay. All right, and then plus c.
Exactly. Yep, that's it.
So is there any area we would want to find with this, or is that it? Is that the end of it really?
For an indefinite integral, we're finished. If we would tell that if we have limits of integration, if we have some value for a and some value for b, we know
Hmm.
we need to find an area, but without those, we're finished. We're done.
Oh, so the indefinite integrals are going to be my friend.
Yeah, I guess that's one way of thinking about it.
Yeah.
So let's do an area problem.
Okay.
I think I want to graph a function first, just so we can have a really good intuitive sense of what we're trying to do here. So sit tight. I'm going to graph this in Desmos real quick, and then I will share my screen when I'm done.
Okay.
So let's say I wanted you to find the area under the curve of this function. Let's say here. Here, I'll just put the integral notation. The integral going from -1 to 3 of negative x cubed plus 3x squared plus 1. It's a definite integral problem. Our answer is not going to be just a function, it's going to be a number. So I want to share my screen. I want to show you what the graph looks like so we can have a good sense of what we're trying to do here. Can you see this all right?
Yep. Oh,
so
wow.
This is our function. Our endpoints are -1 to 3. So I'm going to put x is -1. That'll be right there. So we're going to integrate between this point and this point right here. So between this one and this one, we're only going to consider the area between those two. We're not going to consider anything to the left of -1 or anything to the right of +3.
Okay. Alrighty, let's do it.
Let's go. Okie dokie. What do we want to do first? How do we start this off? I mean, I guess there isn't really steps to do like there are for derivatives. It's just kind of take it term by term. How do we take the antiderivative of this thing?
Well, this is, just like a regular function. So, because it's, addition, whatever our original function was, you took the derivative of each term. So basically we just have to reverse that for each term and then write it, and that'll be our capital F of X.
Perfect.
And then we can use the area formula.
Yep. Show us what that looks like. All right. Well, there's one thing I want. Actually, you did this correctly. So now we just want to apply the endpoints.
Yep, I'm working on it right now.
Cool. So notation-wise, we want to make sure we put the brackets there.
Oh yeah.
So
you gotta
to 3.
Okay, and then okay.
All right. 51/4.
Yep.
I got something a little bit different for that one. So I'm going to try it as well. So I'm going to plug in 3 first. 3 to the 4th power is 81. We have negative 81/4.
Mm-hmm.
Plus this is going to be 27. That's a
Plus
weird looking
3.
7. And then we're going to subtract negative 1 to the 4th power is positive 1. So we have minus 1/4. And then this is going to be minus 1. And then this is going to be another minus 1. So I want to find a common denominator here. So 27 plus 3 is 30.
Yep.
So then this would be 120/4.
Mm-hmm.
And then this is going to be minus 2, which is the same thing as minus 8/4. So we have
I see what I did wrong.
minus 8/4. Do you want to try again?
Yeah, I made a simple mistake. I'll fix it right now and then do the rest.
Go for it.
Oh, that worked out nice, actually.
What'd you get?
12.
Yep. Very nice. The answer is 12.
So these units, could we just say like U squared for units squared?
Well, typically, I mean, that would be the convention, but we typically don't even care about that. We only just usually want the number unless it has some kind of real world application, like if it's square centimeters or square meters or something like that. But if it's just square units, typically we just have the number and that's it.
Okay. Okay.
Great question, though. Let's talk about, maybe we'll do something a little more complicated. Let's go back to antiderivatives because there are a lot of special cases of antiderivatives we want to be prepared for. So I want to start with antiderivative of sine of x. So what function do we take the derivative of to get positive sine of x? If it were negative sine of x, we know the answer would be cosine because when we take the derivative of cosine, we get negative sine of x. But what is it going to be if the antiderivative is positive, if the derivative is positive sine of x?
I think negative cosine of x.
Yep, exactly right.
Okay.
Good man. Let's
Yeah,
kick
I
things.
like these.
Yeah, they're interesting, aren't they?
Yeah, it's nice. It's like a break from taking derivatives all the time, you know.
Derivatives
Now
are so
it's
tedious. Integrals require a bit more thought. You can't just dive into it the same way you can.
yeah. Yeah, so you know, it's nice because you know, no matter how complicated they may look, it's actually you know, if you take it term by term, you know, you can't go wrong.
Let's do something a bit more complicated. How do you
Okay.
do something like this where it's kind of like a reverse chain rule situation? How do you take the antiderivative of the cosine of another function? I want to see if you have any ideas about what to do for this one.
I would say you take the antiderivative of the outer function and then the antiderivative of the inner function. Okay, I think I got it. I gotta just put my thoughts on paper though. Give me 1 second. My dad's calling me.
All right. Tell him I said hi.
Sounds good. He says hi back.
Cool. All right.
And I've almost got this done here. Okay, so I think it's equal to boy, I imagine if somebody didn't like chain rule, imagine how they're gonna feel about antiderivatives of chain rules.
Yep. They tend to be very difficult. So this is actually a completely separate topic on its own. We call this integration by substitution or just U substitution. And like I said, it's a completely different topic on its own. It takes people typically a lot of practice to get U sub right. So whenever we do a situation like this where there's a clear outer function and a clear inner function, it's a big indication that we have to do U substitution. So the way it works is we take whatever the inner function has to be and we call that U. So in this case, we can see that U is going to be 3x. So we set U to be 3x. And then with the chain rule, we always have to take the derivative of the inner function. So we're going to do the same thing here. I know we're doing integrals and not derivatives, but the same concept applies. We're going to take the derivative of U with respect to x, which is just 3. But then we're going to do something different. We're going to multiply both sides of the equation by the differential dx. So we get du equals 3 dx. And the reason why we want to do that is because our integral already contains a dx. We have a dx right there. And our goal is to match this as much as possible with this. If we had a 3 out front, that would be really easy. We'd already be good to go. We would just take 3 dx and we would replace them both with du. But life doesn't want to play nicely sometimes. It doesn't want to give us easy problems to work with sometimes. So we're going to have to manipulate this a little bit to match what we have in the integral. So because we don't have a 3 along with our dx, we're going to have to divide both sides by 3. So we have following. We have 1/3 du is equal to dx. So what I want to do now is I want to take this dx. I want to replace it with something. I want to replace it with 1/3 du.
Why do we what? I'm never mind. I'm just gonna let you finish.
All right. Replace dx with 1/3 du, but then I also want to replace 3x with u because we already set u equal to be 3x at the beginning. So I'm going to rewrite this. I'm going to make this cosine of u times 1/3 du. And it makes things easier. Whenever you have a constant, you can move the constant to the outside just to make things a little bit easier. So I'm going to move the 1/3 to the outside to simplify things a bit. And then what is the antiderivative of cosine?
Sine.
It is sine. So the 1/3 remains. We're going to take the antiderivative. So whenever we take the antiderivative, this integral symbol just goes away and the differential goes away as well. So we get sine of u. And then this is an indefinite integral. We're going to need plus c, sine of u plus c. And then there's just one more thing we have to do. Put u back in. So at the very beginning, I set u equal to be 3x. So this is going to be 1/3 sine of 3x plus c. And then I'd like for you to take the derivative of this and then verify that we get our original function. But before you do that, let me restore this as best as I can. Whoa.
Wait, so with U substitution, um, this is for this, so this is how you anti-derive chain rule, basically?
This is how you integrate the chain rule, yes. This is the opposite. This is the derivative, the integral answer to the chain rule.
Huh,
So
okay.
in order to verify that I did this right, I'd like for you to take the derivative of my answer, take the derivative of this thing and see what you get.
Okay. Uh, I don't think it does.
Let's try it. So I'm going to take the derivative of this. I'm
Well,
going to
actually, can I, before we do that, right here you have the lowercase f.
Mhm.
Um, wouldn't this right here be the lowercase f? So this would be the so the one on the left down there, this one would be capital F of x.
Well, typically I have the function, the derivative is capital F of that, and then the function that we're trying to find would be lowercase. But
Okay, okay,
let's not focus too much on notation here. It's
okay.
really the most important part about this.
Um, well, basically you can leave out 1/3 and then you take the you do chain rule of sine 3 of x. So you get cosine 3.
You get cosine of 3x, but then remember you have to take the derivative of whatever the inner function has to be. So what is the derivative
Oh,
of
cosine.
3x?
Just 3.
Yep, and then what about the derivative of any constant?
0.
Exactly. So what do you get when you simplify 1/3 cosine of 3x times 3?
Oh, just cosine 3 of x.
Exactly, cosine of 3x. So that's how we verify that we did the work right. It's nice having this relationship between derivatives and integrals because it makes it easy to tell if we did the work correctly. The U substitution, like I said, it's really tricky for most people, myself included, when you're learning it for the first time. I want us to practice this quite a bit.
Yeah, that sounds good.
So, would you be available to have maybe the other session later today? I don't know if I don't want to torture you with too much math if you're feeling overwhelmed, but would you be okay to
So
do?
I'll have something from 6:30 to 8, and then after this class in between then I'm going to be working on a history assignment. So if I finish that history assignment in between now and it's basketball practice. So until then, if I finish the history assignment, I can right after practice. I'll get home around 8:30. If you'd be willing to, we could like do it at 9 or so.
Um, 9 o'clock. Let me think. What else do I have? I have other classes after this one. And yeah, let's do it. How about 9 o'clock tonight? That works for you?
Okay, yeah, that works. But I just, on the condition that I finish the history assignment in between now and, by the time I leave for practice.
Oh yeah. So do you think when you leave for practice, you could just shoot me a quick text telling me whether or not you finished the history?
Yeah.
All right, sounds good. So we'll just wait. I'll just wait to see what your text says, and then we'll decide what to do from there.
All right. You'll probably get it around 6:10, 6:20.
Cool. No problem. So we have time for maybe a few more problems. Let's have you try. Hang on, let me find a good one for us to do.
Is this going to be U substitution or just whatever comes to mind?
This one, well, that's one of the hard things about integration. We're going to be learning a lot of strategies, and one of the toughest things about it is understanding what strategies to use and why. So this is a U substitution problem. It doesn't really look like it, but it definitely is, and I'll show you why. Whenever we see a function that we're integrating, we always want to be in the habit of looking to see if one thing looks like the derivative of something else. So we have something going on top, we have something upstairs, we have something downstairs. So we want to see if what we have upstairs is the derivative of what we have downstairs, or vice versa. So what do you think about that? Do we have one thing being the derivative of something else?
Yes.
We do. So what is the derivative of what?
20x to the 4th power is the derivative of 4x to the 5th power plus 3.
Wonderful. So whenever we understand exactly how that works, we want U to be the function that we take the derivative of. So we're going to have U be everything downstairs, or x to the power plus 3. And then we're going to take the derivative of that with respect to x. And we get 20x. And then we're going to multiply both sides by the differential, by dx. Oh, I forgot the exponent there. Glad I caught that. So we have du already. What do we want to do now that we have a clear situation where we have the entirety of du on top? Du is 20x to the 4th times dx. We have all of that.
How did we get the du? We do that process from last time too, again, basically.
Yep, so what I did is we have u, so I took the derivative of u with respect to x. We get 20x plus 0, 20x to the 4th plus 0, and then I multiply both sides of the differential by dx, because the dx is part of the integral.
Okay.
Our goal is to match this as much as possible, and it looks like we matched it perfectly. So now we did the u part of U substitution. Now we're going to do the substitution part. We're going to plug things in. So this entire thing we have right here, we're going to replace all of that with du. So it's going to be the integral of du. That's a weird looking d. Du over, and then notice how this entire thing on the bottom matches u perfectly. So this looks like u prime over u. Now, remember what function we took the derivative of, and remember what special situation u prime over u applies to. Do you remember that?
Could you repeat that one more time?
So remember earlier today when we were taking the derivative of something and we remembered that trick to do u prime over u for a special situation. Do you remember what situation that was?
That was when you have natural log of a function. The argument of a natural log is a function itself.
Excellent. So this is going to be natural log of u plus c. So we have natural log of 4x to the 5th power plus 3 plus c. There you have it. That is our answer.
So du functions as like the derivative of u, basically?
Exactly right. Whenever you have du over u, we can make that natural log of u. But if we have something like this, this does not work. Whenever we have a du downstairs, we know we did something wrong. We know we're going to have to redo it because this just does not work. We can only have du be upstairs.
Okay.
Let's do a little more practice with this. And when we determine that we actually can use U substitution, it also tends to be pretty challenging to understand what should be U and what should be du. So
Well, that's just what you have to figure out in terms of like what is the derivative of the other or what and whatnot.
exactly. Maybe not this one. We don't have enough time for one that's this complicated. Let's have you try this one. This is a U substitution problem. We always want to start by deciding what is U and what's du.
I don't know. Neither of them look to be the derivative of the other.
Well, in this case, we have to look a little bit deeper. You might be looking at this part, you might be looking at this part, but what we want to do is we want to look at the argument of the exponential. See if we have the derivative of this present somewhere in the integral. And we may not have the exact thing. We may not be able to match it perfectly, but our goal is to match it as much as we can. And we're running out of time. Algebra is going to start really, really soon. So I'll just go through this with you real quick. The best thing to do is to move the 36 out front real quick, just to make things a little bit easier for us. So I want to go ahead and make U the entire thing that E is being raised to. And then take, what is the derivative of this?
It's going to be 8x.
All right.
8x dx. If we're, yeah.
Oh, we're out of time. Sorry. Let's continue this either tonight or on Tuesday, whenever we happen to have class next. Algebra is about to start, so sorry about that.
No, that's all right. But yeah, we'll continue this next time.
All right. See you next time. Have a good one.
Yep. See you next time. Thank you. Have a good day.